The law of large numbers is perhaps the most intuitive of the fundamental limit laws in the theory of chance. And part of the reason for its appeal and for its intuition is because it is a law that we are most familiar with in examples. Applications where the law of large numbers is at work are rife around us. So let's take stock of a few of the common examples. We begin by considering again the basic setting, and this time let me borrow from the terminology of statistics. We start with a random sample x1 through xn. What this means is that we have repeated independent trials with the variables all conforming to a common underlying distribution with some common underlying expectation, say mu, and say some common underlying variance, say sigma squared. We promptly form the partial sum x1 plus x2 through xn, what we call S sub n of the sequence. At its heart, the law of large numbers says something about the ratio of Sn to n. Now, the moment we divide the sum by n, what we're doing is forming an arithmetic average of the variables x1 through xn. In ordinary language, we are looking at the mean of that sequence. And since that sequence connotes a random sample, we call Sn over n a sample mean. At its heart, the law of large numbers says something about the deviation of the sample mean from its expected value, mu. The probability of even a small deviation from mu goes to 0 as n becomes large. But it is always useful, when we have a clear statement like this, to retranslate this in ordinary language, because of course it adds a little color to the picture and makes it a little more vivid. What the weak law is saying, in essence, is that if the sample size n becomes suitably large, then the sample mean is approximately equal to the true expectation or mean value, mu. What this picture tells us is that the weak law gives us a principled estimate of mu when it is unknown. The sample mean is approximately the expectation mu, and if it is unknown, we now have a principled process for estimating it. Generate a random sample according to the underlying chance experiment. Form the sample mean, and that should be approximately mu, with a certain error and, of course, with a certain confidence. If this sounds familiar, it is because it is. This is exactly the setting we saw when we estimated population parameters from polls. Right? So, what the weak law is doing is giving us a statistical estimate of a mean value, polls being our prototypical example. In this case, the underlying chance experiment is a Bernoulli trial. You pick a member of a population, and your x's are ones and zeros. What is the expectation that is unknown? It's the population parameter p, the subpopulation of the population in, say, category 1. And the sample mean gives us a good estimate of it, as we've seen. Other examples. A new car has come out and it promises a certain mileage, let's say an electric car, and you get a certain mileage before a recharge is needed. Now, of course, when one purchases the car and one drives it, the mileage one gets depends a great deal upon all kinds of external circumstances. The nature of the driver, the quality of the driver, the traffic circumstances, maybe the weather, maybe the age of the car. All of these are parameters which will affect the actual mileage one gets in any given run. In other words, the mileage one gets is a chance variable. Well, what is it on average? What is the expectation? Well, this is a priori unknown. How does the car company give us such an estimate? Well, the weak law tells us how they might go about doing it. Generate a random sample of runs, take the sample mean, and that should give us a good estimate of an underlying expectation. This kind of setting can be applied to all kinds of consumer properties that one is interested in. Another example is things like calculations of lifetime. If one goes and purchases, let's say, an electric bulb, it will typically come with some kind of statement saying that its life expectancy is so many hours of continuous use. How does one get such a life expectancy? Of course, the usage depends again on many factors. Environmental factors, humidity, whether the current is fluctuating, and so on. Plus, of course, natural variability in the filaments and so on inside the bulb. In other words, the lifetime of the bulb is a chance variable. How does one estimate its lifetime? Form a random sample by taking many bulbs and taking the sample mean and averaging out the lifetimes. And Bob's your uncle. The same kind of time to failure is applied to things of no portent. For example, how long does an aeroplane have in its operational lifetime? In other words, how long before metal fatigue develops and the airplane is in danger of crashing? And again, one in principle does exhaustive tests of metal fatigue, forms independent samples, forms a sample mean, and again we have an estimate. Likewise, the time to failure of a bridge, of a pylon, of a road, or a building, or anything, whatever, what have you. Right. Still other examples. How does one form actuarial tables of risk? For example, the life expectancy of individuals. And again, this is a chance-driven process. If one forms a sample mean, we get an accurate estimate of the underlying life expectation, provided, of course, our sample is large enough. The law of large numbers also gives a firm foundation for the theory of fair games, and the prototypical example here is gambling. Right? Imagine one goes to a casino and one wants to play repeatedly in some game of chance. One pays a fee to partake of the game, and when one plays the game, then one wins or loses a certain amount of money. The expected losses or gains is governed by a parameter mu. Now, what should the casino charge for you to play the game if it is known that the expected winnings are mu? Naturally enough, we'd say that the charge for a fair game should be mu per trial. If your expected winning is mu, then you should be charged mu, so that your net expected gain is 0. And that would be a fair game. It's not biased or skewed in one direction or the other. The weak law gives us a firm foundation for belief that this actually is a principled and good strategy. One should be a little cautious in how one interprets the weak law in this setting. Right? It is saying formally a very precise mathematical statement, that the probability that in absolute value the sample mean deviates from mu by more than a tiny epsilon is small. It does not say that you are guaranteed to not win or not lose. No. The devil in here is in the details. Right? And it is true that we've hit this with a fairly blunt hammer in that we've normalized it by the factor n. And over a long number of trials, lots of details are hidden in that large n. This will take us a little too far afield, so I shall not get into this. But it is in principle possible to construct a fair game where one pays a fair entry fee of mu each time we play the game, and construct it in such a way that one is essentially guaranteed to lose lots of money. Right? So one should always take a mathematical pronouncement with some caution. Remember, the mathematics, the terminology, the definitions, and the results, when applied to the real world, are models of the real world. To the extent the model captures the essential features of the phenomenon under consideration, we will get accurate and good results. To the extent that the definitions miss a key feature, to that extent, then the applications become suspect. I will leave it to the student to think of other applications of the weak law of large numbers. The next time she opens a newspaper or listens to a news report and she sees a number thrown out, perhaps she might be tempted to ask, I see, Here's where the weak law comes in, and this will be a useful and instructive way of thinking about the weak law as you go forward.